thank Shiraz for approving my visit here and a visit to give the opportunity to talk. So, I am giving a seminar on the Kite diagram through symmetries of Feynman integrals. So, this work is motivated from this 6-7 papers from Barack Cole, my postdoctoral advisor, and one paper which we finished with him. On this paper I will talk. So we all know that the Feynman diagrams and the associated integrals are the computational core of the quantum field theory, and their evaluation is very important in physics. There are two or more well-known methods to compute these Feynman integrals, namely integration by part method and differential equation method. So, Barack Cole some years before devised a new method which is closely related these two older methods called the symmetries of Feynman diagrams, which exposes a novel symmetry group associated with a Feynman integral which acts on its parameter space and foliates it on different group orbits. So, suppose we consider a Feynman diagram I and with a fixed topology. So, the Feynman integral will depend on some parameters. The parameters will be the mass squares flowing in the propagators, and if there are some incoming momentas and the kinematic invariance built out of that. So, that whole thing I denote it by capital X.
What is fixed topology?
Fixed topology means I am considering one Feynman diagram. I am not changing it. It has a fixed topology. Yes. So, given a Feynman diagram, so SFI, by SFI I mean the symmetries of Feynman integrals, defines a set of partial differential equation which the integral itself satisfies, and the idea is not to solve this the Feynman integral, to integrate and solve it, but to
Hello.
Yes.
So Subhajit, will you be talking only about the scalar integrals, or will you be also talking about integrals in vector space and so on?
I will be only talking about the scalar integrals, but in principle in this method one can talk about fermion integrals as well, but no computation had yet been made in that direction, but it can be done.
So this integral is probably only a function of the Lorentz invariance.
Exactly. Lorentz invariance and the mass squares in the propagators. Okay. So, yeah. So, as I said, yeah. So, see, these two methods are this integration by part method, which is most similar to the method which I will be talking about, and the differential equation method is like they set a recurrence relation between Feynman integrals. They integrate by parts, but in those methods what was absent, that for which diagram it will be completely useful, that thing was not there. So, the symmetries of Feynman integral, as it associates a group, it will tell you for a certain diagram whether it will be good or not, and you will see that it will show that a particular Feynman diagram with a fixed topology can be evaluated through a line integral over more simpler diagrams. By simpler means, suppose I have 5 propagators in my diagram which I am talking about, it will have one less propagators, and also in some particular locus in the parameter space you will see that this integral will be just not the line integral, but only a linear combination, not even a line integral. It is much simpler. It will be linear combination of simpler integrals. So, this is the novelty of this method actually. For example, this integration and part by part, these are very old techniques to use these QED propagators and many things actually, Smirnov and these people. So, as I said, this SFI methods has some geometrical symmetries, and it defines a continuous group G which acts on its parameter space. So, as I told you that this generically this symmetries of Feynman integral reduces a Feynman integral over a line integral over simpler diagrams up to some initial conditions and so on. X is the parameter space. Suppose you have a Feynman diagram set of parameters. So, it has some propagators and it can have some external momentums. Those are parameter is the mass square flowing in each of the propagators and the kinematical invariance or the Lorentz invariance made out of the incoming momentum. These are the sets of parameter which the integral will depend. Okay.
So, I have a question.
Yes, sir.
Yeah. So you know, like when you're talking about the symmetry of a Feynman integral.
Yes.
Is it the same symmetry group as you know, like the group that we calculate when we calculate symmetry factor, like the more the symmetry a Feynman diagram has, you divide by a larger symmetry factor. Is that the same symmetry group or some other symmetry group?
I mean, it is a symmetry group. I mean, I will define some equations which this integral will satisfy, and you will see that in this parameter space there is a continuous group which this integral satisfies actually. So, this is the symmetry.
So, this is a continuous group.
This is a continuous Lie group, yes.
Okay. So, it is not a symmetry group.
No, no, it is a continuous group acting on the parameter space actually.
But is there a relation between these two groups?
Is there a relation between these two groups?
For example, it is like, you know, the finite group
Sorry?
of A group or B group.
I don't even know what the group is going to be.
Yeah, I will show you. Yeah.
Okay.
Yes, Loka, you were saying something?
No, maybe you would tell us what the group is in user.
Yeah, I will tell you. Yes.
Okay, and then maybe I can ask the question.
Okay. Yeah. So as I was telling you that this SFI reduces the computation of Feynman integral to a line integral over simpler diagrams up to some boundary condition or initial conditions. So, at some particular locus on this parameter, suppose this set of parameters has a relation between them. In that locus, you will see that the equation set is not, I mean, rather than differential equation set, partial differential equation set, it produces an algebraic equation, and then the solution to the integral will be immediate. It won't be a line integral even. So, this SFI method before this kite diagram was studied were applied to different diagrams for more simpler diagrams. For example, this diameter diagram, this diameter diagram, and this one loop propagator diagram, for example this, and a bit non-trivial this vacuum Seagull diagram which looks like this. And in this in this diagram, this is a three loop diagram. For three are completely arbitrary masses, the solution was completely generic with some special hypergeometric functions, some generalized hypergeometric function. You can see the analytical answer was gotten from this method actually.
So you have both phi 2 and phi 4 interactions in the theory?
So, see, I am not concerned about some particular theory, I am just talking about a Feynman diagram.
Okay.
I mean, I am not looking to a particular theory, because you will see that in the different propagator different masses are flowing. So, it will be a complicated, you know, like UCD and so on. So, fake UCD, something like that. Yes, I am talking, I mean, I am considering the Feynman integral in arbitrary space-time dimensions, d dimensions. Yeah. Yes. Yes. But whether, suppose you give me a diagram, I cannot 100% assure you that this method will extract the answer in full complete generality, but this method will tell you that whether it is good for that or not. And for many diagrams it has proven to be good actually. Okay, so these were the diagrams where it was successfully applied, And in this talk we will consider the kite diagram, which I will show you why it is a kite. So, this kite diagram I will show you what it is, appeared in electron propagator renormalization of QED, where a single mass scale was studied. Because this kite diagram you will see there at most it has 6 parameters, and in this computation we have considered it to the most general order. So, it has all 6 parameters. In this case it was studied only where there was a single mass scale, others were 0. And this integration by part method, which I think you were asking, that it showed that it can be reduced in a completely massless case to some linear combination of some simpler integrals. And in QCD in 4D it was reduced to some line integral over logarithmics, and there it was called master diagrams and all. And also in 3D massless version of this diagram, it was found to be essential in the second post-Newtonian approximation in 2D problem. If you see the potential between two black holes, you will see this, and there it was called some lizard eye diagram. It looks like that. Okay. So,
how do quantum spaces integrals come about in the think about the post-Newtonian approximation?
actually there you have to do this tensor algebra, and you will see that you can convert this interaction of two black holes through this diagram occurs. Actually there are some tensor algebra involved in that actually, and there this kind of, I mean this diagram, this kind of diagram appears. So, second post-Newtonian, it is second post-Newtonian approximation actually.
So where is the parameter for this approximation? So I didn't quite understand how do you get there?
I mean I am saying that when I am considering this diagram only, I am saying it appeared when all the masses were 0 in computation of second post-Newtonian approximation between.
Is that the quantum field theory is path integral interpretation?
I don't think
Or
so.
is this the formal integral that appears?
Yes, it is one of the integrals that appears here. Yeah, it is just a mention that where, I mean one can ask where do you see this diagram earlier, whether it has been studied or not. I mean here it was completely massless. I think it is the second one. Yes, I think so. I think so. Yes.
Like, there is this particular way of doing the post-Newtonian approximation by diagram matrix. That goes for generalization. That is the context where we talk about.
Yeah, maybe, but it's not done there with that. That's why.
Yeah. So, let us consider a Feynman integral associated with a diagram with L loops, P propagators and N external legs. So, as I said, it will be a function of the mass squares and the kinematical invariance built out of the external momenta, and the integral will look like this, where K is defined like this, a linear combination of the loop integrals and the external momenta. So, this will be the parameter space, namely the X of this diagram.
These are only diagrams and you don't have derivative interactions. You are assuming the vertices just give you some multiplicative factor.
Some multiplicative factor, yes. Yes, yes.
No factors of momentum.
No, I mean even if it is, it has to be a Lorentz invariant. Then you will get less number of equations. You will take a linear combination of equations and you will throw them out.
But if in principle I could also have terms that look like Ki dot AB.
Yes, yes, you can in fermionic consideration. When you will,
Even in scalar, if I just have derivative.
yes, even then it will be. But I am considering like this. But then it also can be applied. Then you will have less number of equations. You have to throw them out and so on. So L was the loop momentum, and we know as it is a loop integral, if we shift the loop momentum like this, it should not affect the integral. So we will get an identity by Gauss's law and so on. So all of the operators looking like this will act on this integrand and will give you 0. So this will give you a set of partial differential equation which the integrand will satisfy. Okay. And each of these operators or a linear combination of them will give you the group actually.
Sorry, the change of execution variables will affect the integral. So it's being assumed that you are only considering finite integrals.
No. I mean, if you do this shift, you will get two terms, and this term will remain, and another will be a boundary term. So for small enough dimensions, it will for a large enough surface, you can throw them out, and you can show that this integral will satisfy this identity.
So you're defining your integrals with dimensional regularization?
Yes. So suppose
So dimensional regularization always exists.
So dimensional regularization, what it does is it translates the divergence into this D plane, right? And you can analyze them further actually.
There's always some dimension, some formal dimension. Yeah.
So that was the idea why people called it integration by parts. You throw away the surface term actually, the boundary thing, something like that.
So that's not a boundary term, this is what you were saying.
No, this is not a boundary term.
Like derivative acting on what?
The derivative acting on these both two things.
This is the boundary.
I think what it means is the boundary term is 0, and therefore the sum of the two terms. Now we'll act with the derivative.
So that's why.
Two terms.
Yes, I mean that is in some sense an equation actually. Yeah. Because when this will hit this will produce something, and when this will hit this will produce some other thing. Yeah, that I am going to show you. Suppose you do something like this with a generic Feynman integral, what happens we will see. So if you do like this, you will get these two terms, right? When the integral will hit the momentum, it will get a delta function, and the other things will look like this. Sorry?
What was the first equation? What I tilde?
Oh, sorry, I tilde should be upstairs. Sorry. There was some typo.
LB is also a derivative index?
This del oh sorry, this
I think LB is
no, this is like this. This is like this. Sorry, sir. Some typo. So this will produce these two kind of terms. So now what you can do, you can express this numerator, as Prahar was pointing out, like this, right? You can express these terms with the help of the propagators. Then there will be propagators here with some additional masses, because you subtract and add. And then if you simplify it, it will generate two kinds of terms. You see here this propagator and this propagator cancels out. So this is giving you a derivative of a simpler Feynman diagram. One propagator is getting out. Okay? And this you can think a derivative of the Feynman diagram itself. Is it making sense?
So this is the first equation I'm going to see.
So
second term of the first equation.
Yes,
You were hitting just a propagator,
I am hitting just a propagator.
and then you got that ki squared minus xi, the whole thing squared as the numerator.
Yeah.
And then that I tilde has the propagator removed from it.
I tilde, yes, actually that propagator is not there. That propagator is squared.
Yes, so I tilde is not quite I tilde. So I tilde with the propagator removed.
Yes.
Okay.
Yes. Only then this cancellation will happen, right? So x is the mass. X is the mass in the propagator.
So what should we consider A is the unit of length, and I is the of length.
Ki means, there are several propagators, right? Yeah.
The index value of
Yes, yes, yes. Yeah. For example, suppose what will happen? You have a propagator something like this. Suppose you hit it by this. What will happen?
Yeah, maybe you know like you can skip both.
Oh, I mean, is it a dark issue loga or the board is not visible at all?
So the camera is not affected.
Oh my.
Okay.
এটা তো আমি-
Okay, so you're only going to differentiate those propagators through which the L8 loop momentum comes.
Yes, 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 yes. For some other generator, some other propagator will be here.
Correct. Yes.
Right. So suppose if you differentiate like this, it will make it square with a minus sign, and then in upstairs you will have some 2 L dot P,
Yeah.
something like that. And now I express this L dot P with the help of the propagators again.
In that case, I-tilde is I-tilde. Remove the
Let me
propagator square.
No, it's a square.
It is a square, no?
Oh, you're taking out.
Yeah, yeah, yeah. It's a bad notation. Sorry.
Yeah, it's just a propagator. Right?
Yeah. So now if you express this thing like this with the help of the propagators, see there is a factor like this in the denominator, which I mean this kind of things are there in the denominator, and you are expressing the numerator like this. So in one case what will happen, it will just cut upstairs and downstairs like this.
Sorry, what role is LB played? On the left hand side there is an LB.
Yes,
Where is LB on the right hand side?
Again, this
No, in the next equation.
in the next equation.
Yes.
I mean you see this k is a linear combination of L and
all the other.
yes, yes, yes.
I see.
I mean if I for a simpler diagram,
No,
if
why
I,
don't you give us one example?
yeah. Let me give you the simplest example. So this is just this, right? So suppose this is mu. Good. So now here only one operator will be there, which will be this. So when this hits this, these are all mu's, okay. So this is a d, and here is the integrand itself. So okay. So now what I will write, this 2 L square I will take 2 common, and I will write like this. You see, when I cut, one thing is cut, it is giving back you the same equation, right? Plus m into this, you agree? Yeah. So as this was a simpler diagram, there is only one equation. If you carefully see, this is the Euler equation which brings out the dimension like this. No, this is d dimension upstairs and 2 dimension downstairs. So this will be minus, sorry, there is a minus sign. So this is the simplest example. Suppose you have some more L plus P whole square, some more complicated Feynman diagram, then you will see there will be more this kind of operators. There will be same L1 del del L1, L2 del del L1, many things. So there will be many this kind of sets of partial differential equation which the integral satisfies.
And suppose you had L1 and then dot some. Can you do one more example with one with 2 properties?
Yeah, sure. Yeah, no problem.
One more, you didn't necessarily have to take L mu, the mu to be the same. In principle,
No, they are different. Yes.
the fact here you contracted the 2 mu, right?
Yes, because here I didn't have any other option, because it's just one L. Yeah. which diagram should I take? For example, this. Okay. So suppose I am, this is squared, this is okay. So now there will be these kind of operators. So L del del L. This is not a good example probably, because for external momenta the thing is bit different. For external momenta we consider an identity. For example, yes, 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 yes. That would help actually. Good. Let me do that. So this is the integral. So now there will be these kind of operators. Integrand, this thing. The same. Yes, yes, yes. For simplicity, I am not writing the index. These are all dots.
But in general, you would still get equations with mu and mu arbitrary.
No tensor set of equation. Always there are no free indices. No free indices.
That's how we are able to calculate the boundary, right?
So for example, let me do one of them because it's long. So suppose let's do this. So this, when it hits this, it will give a D and the integrand back, and if you consider the loop momenta, this is the integral itself. Okay. The next term is so
why don't you show us the term where L2 hits?
That will be easier.
The L2 minus L1, where it hits that.
So suppose I take this thing.
No, you can take L1, but it hits the middle problem.
Okay, good. I am writing just
Just that.
Just that term.
I see. You make it a sum of L2 minus L1 the whole thing squared and L1 the whole thing squared.
Yes, yes.
And each of them will cancel different.
Yes. And something will remove the propagator itself, and there will be that propagator square remaining. So that is a less complicated Feynman diagram. So one propagator goes away, and if you will ask why there is a square, that you can think as a derivative of mass on that diagram, that simpler diagram. So this is the idea.
Right.
So like this, many equations will generate, right?
Right. See, make simpler diagrams.
Yes,
Complicated
yes.
Diagrams possible.
Yes.
Sounds very.
Is it okay?
Yeah.
Okay.
Sorry, can you just repeat what was the understanding of how we deal with this L2 minus L1 propagator?
So, oh, okay. Always this is dotted. Huh? So, see, there will be 2L1 dot L2, Loga, can you see?
Yes.
And there will be L1 square, 2L1 square. So, a 2L1 square I will write with the help of this, 2 into L1 square minus 2 mu 1 plus 2 mu 1. And 2L1 dot L1 dot L2, I will take help of this diagram, this propagator and this propagator. I can generate that cross term, right? So, the numerator I can write with the help of the denominator. I mean, denominator means the propagator.
All of them.
Yeah, all of them, yes.
You write a linear combination of the denominator terms, and then each one of them is a simpler diagram from this point of view because it cancels one.
Yes. Sometimes it gives back the diagram
Same
itself.
one, because the square gets cancelled.
Yeah.
The square gets cancelled, and then that's like the homogeneous part.
Yes, exactly. That is the homogeneous part, yes.
So what would be the equation for this sunset diagram?
Sunset? Oh,
What this diagram, what is the equation for this?
the equation is long, I have to do all the calculations.
So roughly what does it involve? It will involve derivative with respect to mu1, mu2, mu3.
Yes, and sometimes it will multiply d with the integral, and sometimes the sources of this will be, you understand, right? This will be this diagram, because if you contract this propagator, it will be like this. If you contract that propagator, it will be something, this thing. So these are the sources of this diagram. That sources means, let me write a generic form of this kind of integrals. So as there are many, there is a set of integrals, I am giving it an index, okay. So these are the form of the generated integrals, where C can be the dimension or d minus 2, something like that. And this is the,
C is a number, right?
C is some number, yes. I is the integral, Tx is the matrix.
You get a homogeneous differential operator acting on your integral, and then on the right hand side there are other integrals. So these other integrals are simpler integrals. The simpler integrals are what is called the source.
Yes, this
So
J.
the differential equation in terms of parameters, homogeneous differential equation, and whatever is on the right hand side is the source, but that's simpler. That's clear.
So what is this T,
Capital
capital T?
Tx, if you write this, all equations, the equation will look like this.
Like the derivative with respect to the mass analysis.
Yes, and there will be many things, x1, 2x1, something like this, and there will be del x1, del x2, del mu1, del mu2, del mu3. It will be some j1, 2, 3.
So the T is also just numbers which is independent of x.
No. If you consider only T, that you can think of a numerical matrix, but it is easier to consider this Tx as a matrix, which depends on x, linearly in x.
Okay, so T is a matrix which acts on the column of x.
Yes.
Then contracts the del by del x.
But If you can forget about this, you can call this T, which is an x dependent matrix, which multiplies the column of del del x.
But it depends only linearly in X.
Only linearly in x means the mass squares in the mass squares. Yes.
Okay. And C is independent of X.
C is independent of x. C is the number like dimension or dimension minus 2, something like that.
And the J is, so what are the kind of diagrams that occurs in J? You're telling something about removing a propagation.
Yeah. Let me tell you.
If you do the proposition, there is a square term also, right? So the denominator.
Doubles.
No. That square you will think of a derivative with respect to mass.
Okay.
Yeah. It's a mass derivative of a simpler.
Of a simpler diagram.
The reason why first trick wouldn't work is that if you have a tensor in the numerator,
Ha.
you can't write it in terms of
No.
denominator.
No.
But one quick question.
Huh.
It seems like naively you should have A, B equations labeled by index A and B, right? Because you can take
No.
del by del LA
Yes.
mu dotted with LB times I.
Yes.
mu.
Yes.
So
Then this
A-
delta AB will be 0, no? This is Kronecker delta.
Right, but in principle you have a whole tensor worth of equations.
Yeah. That's what I am writing, no?
Today you only have one index.
Oh, maybe I messed up the indexes. There are two index. There are two index here. But if I write the equation properly, you will see. Yeah. You can see the equation here. Have I
I
written it?
also just mentioned one.
Oh, just a moment. You correct in the equation must be there somewhere. Just a moment. So you can think this Tx matrix like this.
But it only has one index. I'm just wondering.
Yeah, the equation has one free index only, right?
Right, but if I have A is the number of loops, A is the index counting number.
Yeah. Just a moment. I will tell you. Just a moment. Maybe I am messing up with the index. Just a moment, okay. No, let me write the equation correctly for him.
He's written 4 equations over there.
Just a moment. This Tx is a matrix, right? It has two index.
The entire equation.
Entire equation has one index.
That's what I'm asking.
No.
You're taking derivative with respect to one L
Yes.
and you're putting an explicit factor of another. That's what he's asking. You put an LM and del by del, LB and del by del LA.
Oh, so why?
So right now you gave this example.
Yes.
Where there were 2 loops.
Yes.
But you wrote down 4 equations.
Yes.
Right? So I might naively expect, maybe there's some symmetry factor.
No. Tell me.
Naively you might expect there to be n squared number of equations if there are n loops.
Oh, okay. So you see, the operators, there are some certain number of operators which you can operate with. For example, as there are 2 loops, there will be this kind. The operators looks like this. So there will be, for example, there will be some. So how many will be there? So there will be L1 del del L1, L2 del del L2, right? L2 del del L1 and L1 del del L2. So this each of the operators I am denoting by this A.
Oh, so A is not a loop.
A is not number of loops.
No. A is the number of equations which you can generate out of this.
Then your notation is a bit confusing because you were saying LA. So then that
Oh
means
my.
be a loop.
No. Oh.
In that first equation that you wrote down.
Oh no, don't confuse this A with this A. These are the number of generators, I mean number of equations which you can generate actually.
So that is more like A.
Yes, yes, yes. So, for example, you understand that in some of the equations this will vanish because L2 del del L1, this is just Kronecker delta. So sometimes this C will be non-zero and sometimes this C will be 0. Yeah. So this is sorry for being so. So this is how the equation. Yes, lower.
So can you just draw me the diagram that you brought on the board?
Yes.
What are the diagrams which contribute to this code?
Yeah. Yes. Of course.
And how do you figure it out?
Yes. Should I draw the diagrams which my diagram has, or only the diameter?
Yeah, for that, what is this diagram that you?
Oh, so this is the diagram to start with.
Okay.
So the sources will be when you remove one of the propagators. So you can remove this propagator. So this will give rise to this. This will give rise to this, right? No. Yeah. This is like this. Oh, this.
But with the 2 mark points,
Yeah, the 2 mark points.
we got rid of the middle property.
No. This one.
Yeah, but we need 2 mark points, where that propagator would have been.
Oh, like this you mean? No. These are do not have any propagators. Yeah. So one is certainly this. Yes.
Okay.
And
the other one, this circle that you have drawn is the thing that occurs as a self-energy connection in the Feynman theory. Is that
you can
correct?
think it like that, but I am.
No, I think it's only this 8 times that.
Yeah, this one will be all.
No, you can no. That if you only contract this, right? You can also contract these propagators. For this, so for example, suppose give you a complicated example. So suppose you have this diagram. This will be good for understanding. Suppose you have this diagram. You see there are 4 kinds of propagators which are in the same fashion, and this is a bit different. So what will this will give rise to? Yeah, propagating seagull 1. So if you contract one of these 4, all will be same. I am drawing just one. There will be 4 of them. And if you contract this will be figure 8. Only these 2.
Okay.
And fortunately, I am considering this diagram in my talk. That's the kite diagram, but it does not look like a kite. But if you view it from your inner eye, it will look like kite. This is kite. Yeah, because in the earlier literature, this was sometimes called kite integrals and so on. So that's why we called it kite actually. Otherwise, we planned to call it marshmallow diagram.
So in your earlier example, when you took out one of the the stuff that you threw just as one.
Yes.
That is one circle with 2 mark points or not?
I mean, I am getting confused about that. Why I am getting confused? Because you see, all the propagators has different masses, right? So there must be a. Oh, will it be like this? So these different masses. So suppose I contract N3. Sorry. Yeah. Actually, there is a chart where you can see that which diagrams is sourced by which diagram.
How do that make sense? If I start with the diagram which is convergent and I get sources which are divergent,
Okay, so I mean, while considering the SFI, I mean, we don't bother about the divergence at this moment. That what about the divergence? We just express the considered integral into a line with the help of the simpler diagrams with a line integral. But as I said that in this one of these diagram, this bubble diagram, I was not involved in this calculation, in that calculation. In this bubble diagram, there are many, there is a discussion which Barak wrote, which describes the divergences, whereas the main idea is that to do dimensional regularization, where you can transform the singularities into D plane and then you can analyze it. Yeah.
Superficial integral divergence concept, because some number of things.
Yeah, but when you contract, you will get divergence.
You know, something like what you're saying happens if you just do fractionation by part. I mean, if you have 1 over x minus a times x minus b, that's 1 over x minus a minus 1 over x minus b to some power. The divergences are reduced, right? What happens there is that each of the second diagrams is more divergent, so the divergences cancel.
Yeah.
So that must be something like that must be the case.
Yeah, but I guess one wants to think of the closeness as individual diagrams again, right?
Yeah, but then if you've got a good regulation scheme, you just forget about it.
And you see, for this propagating seagull also, you can derive this method, and I mean other collaborators with him actually are finishing this computation, where you can also express this propagator seagull. Yeah. Because you see, this I told you as a vacuum seagull, you can see this as a sun and a seagull like this. This one doesn't look like that. You can imagine something like that, that a seagull is there. Sorry, should I? Okay. Yeah. So, see, as I told that the differential operators, differential operators are like this actually. So, in principle, you can, as I said, that you can express this the solution of this integral from as a line integral from point A to B, and this comment I will come later. So, if you see that this differential operator, if you take these commutators of this makes, I mean, this gives rise to a group actually.
But what this line integral is basically because it's a first order differential.
First order differential equation, so the solution is a line integral, and in some cases you will see the line integral is even not there. It is only a linear combination of simpler diagrams in a particular locus of in the parameter space.
So what equation are they solving?
That equation we are solving. Yes.
What is unknown?
I is unknown.
And
J is the simpler sources.
Suppose imagine K, yeah.
Suppose, yes, exactly.
you do it recursively when you
Yes,
know
yes.
the algorithm before the unknown.
Yes, yes.
Okay, this is true for general diagram, but this equation you are bound to get for general diagram.
But for all general diagrams, you won't get. I mean, one equation is always guaranteed. That is the dimension equation, like the Euler equation for partial derivatives. But as I said, that I am expressing. I mean, when I differentiated, there were some numerators. I expressed them in terms of the propagators. But for all diagrams, for example, this is a bad diagram for this Mellon diagram. Always not possible. For here, you will only get this kind of equation, only one equation. You cannot get more than one equation looking like this, because you will get something else. There are 7 equations. I have to draw it. Do it actually.
Maybe not every quadratic form appears in it.
Yeah, you cannot express them with the help of the
Suppose we do some counting.
Yes.
Yeah, you cannot cancel.
Yeah, so not every quadratic, but it depends on being able to express every quadratic form
with the help of the
denominator.
yeah. I will count that. One can
characterize that by vertices or something like that.
No, one can characterize that by the number of quadratics by the number of propagators. If you take that quotient, you will see that how many you can do. If the quotient is 0, it is maximally
Number of quadratics what?
number of quadratic, number of Lorentz invariants you can quadratic forms, the kinematic invariants.
Okay.
And how many quadratics in the propagators are there in the denominator. If you take the quotient of those two spaces, that will give you that how good is your thing for that diagram or not. For the this diagram, you will see the quotient is 0. So, that is maximally useful. You can actually, if you get the answer for this diagram at any base point through a line integral, you can explore all the parameter space because that quotient is 0. So, this is maximally effective for this.
So you can still put it into J as you were saying. You
No,
can
no.
simulate some derivative interaction. Right?
Not always, not always. If you do the computation, you will see.
I was asking, wondering if this can be done at the level of the full portable conflict in getting equation of the quantum secure.
Yes, I understand what you are saying.
You get it. Like a derivative interaction term is a different integral. I mean, it's not a simple integral. If you want everything else to be simple,
And what is this change?
and it's not a pure denominator.
Some more complicated thing will come.
Keep going in the original state. I think it must be useful if everything apart from your diagram is simple.
Yeah, exactly.
Because your diagram, the differential operator in your diagram, and then everything on the right hand side should have pure denominator.
No, but just to get an equation,
You get, I think you'll always get some equation. So there may not be for that point of view.
But we are calling
that
this.
can be done in the whole set
Yeah.
of diagram.
Yeah. The equation set will be there, but the sources will be not quite the source which we are calling sources actually.
I think you'll always get an equation.
Yes, we will always get an equation.
My question is, can you organize all
Because
this to, if the equations on, let's say, because they are getting different vertices, presumably relates different type of theory.
Yes, probably.
This is what's to set up a bootstrap program.
But for any diagram, one equation is always guaranteed. The dimension into I is this xi del xi on that diagram is equal to 0. That is always guaranteed. But if you get one more equation like that, you are gaining. You are you are starting to gain. Hi. Yes. Contracting the loop lines. Yes. Huh? Huh? Yeah, but I haven't. Yeah, maybe. Yeah, that would be good actually if something comes.
Subhajit,
Yes, Loga.
so is there an example in a terminus with one diagram and this group?
Yes, I mean when I will talk about this diagram, I will tell you the group. This will be the group of upper block, the triangular invertible matrix like this, something like that. I will tell you.
So, but let's say one loop, something simpler, is there I mean, how does the group look like for, let's say, one loop diagram?
For one loop diagram. Then the group is pretty simple. What will be the group?
What do you mean by? At the moment we see differential equations.
Yes.
Where is the group?
So the group is, so this matrix, this forms a group actually.
So ignore the sources
Yes,
and think of the differential operators as generators.
as generators of group, Lie group actually. That is the group. That is the group.
You can make a connection. I mean, you have, so, how are you going to solve this? You have some differential operator like that, and then you have the space of your x variables. Okay.
Yes.
And then you have some reference point on the x's, and if you want to find out the integral.
Yes, that is the basic idea. But here what we will do, we will do some clever tricks. Yes.
However, first of all, maybe this is clear by construction, but you will do a line integral.
Yes.
And it should not depend on the choice of the line.
No.
So that requires, that requires showing some integrability condition take, you have this bunch of differential operators. They are commutative to the zero.
Yes.
So is that like inbuilt in the construction, right? Otherwise, how are you going to solve this?
Yes. I mean,
Meaning that the field strength, the field strength in this space should be zero. Otherwise,
you have zero commutator, some kind of zero probability.
yes.
But then they won't be algebra. No, they won't have a.
Okay, I don't understand the algebra thing, but I can see that T fellows are like H fields, and they're, all I mean is that there is a unique, answer to this solution.
yes, yes, yes,
And it should not depend on the line that you see.
yes.
That requires the commutator to be the linear combination. A, comma, D should be specially because the average
How do you see this SATC, like, how do you compute for equality?
that depend on the integrals that one considers.
But maybe if we let Subhajit go on, we probably
Yeah, please.
Yeah. So, I mean, I won't be solving only the thing you said, the line integral. I will do a more cleverer thing here.
Right.
So what?
Yeah, why don't you show us what you have, then we can ask questions.
Yes, sir. Yes, sir. Yes. So that's what is the next slide. Suppose you have a left null vector to this T matrix, which annihilates this. So then you will be left with this kind of equation, right? If you find the left null vector, I will tell you how to systematically find it. So you will have a very simple, this is no more a partial differential equation, this is just an algebraic equation.
It annihilates the derivative.
Yes.
Okay, fine.
So now if you find that the solution is just a linear combination of simpler diagrams.
Right.
Now the
Left null vector is algebraic.
yes, algebraic thing. But there is a systematic way to find, one can do it by direct solution, but there are some systematic way to do that. So
Left null vector of the matrix T.
of the matrix T, yes, which get rids you of the partial differentials.
Right.
Then converts it to the algebraic equation, and this is this is called the algebraic equation, and this is the algebraic solution for that integral. So let me tell you how can you get that. So for example, to get this left left null vector, one can do the maximal minors of that T in the linear algebra, you know, right? I mean, if there are more than n, suppose a rank of a matrix is n plus 1 cross n. So there will be a linear relations between this. The maximal possible rank is this. So you can find a vector LA which can sorry, can I remove this some sorry, which one, sorry? Degenerate means? Yes, yes, that can be 0, that is known as the global stabilizer. So what that will do, that will put a constraint on the less complicated sources. That is the global stabilizer, that is the interesting part. So for example, if you find such a null vector which annihilates both of these, then only Ka dot Ja will be 0, right? So this will set, and which should be true, because this diagram should satisfy this condition. So the idea is you can do SFI equations for these diagrams and substitute its derivative from those equations, and you can manifestly show that this constraint is obeyed. But for this kite diagram we have not been able to show that, but for other diagrams this thing which I just told you has been shown actually.
Basically, we have this net null vector if the number of equations is more than the number of parameters.
Yes. So, it can be obtained by this, and there are also, I mean, from maximal minors, and there are also factorization of this maximal minors which also tells you about the group invariants and all. I mean, it is, I mean, if you take, you can show that if you obtain the maximal minors of that T, that maximal minors can be factorizable with the overall polynomial. This is dependent upon the diagram you are talking about, and some orbit means some polynomial which should be equal to 0 times yes, and the stabilizers mean the left null vector actually. So, this maximal minor can be factorizable in these 3 parts. So, at this equal to 0, if you dot with this thing, then your T will vanish.
Right. Now, in your kite diagram, you have 2 loop momenta.
Yes.
You have total of 4 equations.
No, there are 7 equations because there are external legs actually.
Oh,
so there.
External legs also. Okay. Would you differentiate only with respect to loop momenta?
Yes. P dot del del L1. P dot del del L2.
Go into what you differentiate.
Yes. Only the loop momenta.
Only the loop. Then why?
Y7. 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 Yes.
What's that? DL.
No.
There is no real there.
Which?
You put L1.
Ah.
No.
Let me write. This is good.
Yes.
These are the 6 things, and there is an identity.
What is P?
Incoming momenta, external momenta.
This is a Prahad.
Yeah,
Related Prahad.
that's the tensor stuff.
There is a tensor. You want overall scalars, but you can use external momentum mix.
And there is one identity. You see, my integral is a function of p square and these 5 things, 5 mass squares.
Okay, great. So in this case, let's say you have 7 equations, and I just wanted to understand 6.
No, 7.
But he's claiming with 1 more.
No.
Okay, whatever reason. And so that's your A indices will run from 1 to 7.
Yes.
And your J indices now will run from
1 to 7.
1 to 7?
Yes.
J should run from 1 to 5.
No. There are 7 equations.
No, that's fine. But J is the number of parameters, right?
Which J? Sorry.
Look at your equation.
Number of masses.
Oh, this one.
Yeah.
That's the number of
Masses and presumably P square. outside.
Yes.
So 1, 2, 3, 4, 5, 6.
I am telling you about the why you will get p square here.
No, but how many indices are there?
6 indices.
Six
6 indices.
So yes, A is running over 7, J is running over 6. Therefore, you're guaranteed to have 1.
Exactly.
Then where is the 7th equation?
Yes, I was just going to tell you. Suppose you do this. This is true. And this understand these integrals to be functions of these things. So now I do both sides same thing. am not writing the measure, it is
Why
too
not
complicated.
tell them P?
Yes, I am both sides I am doing this. Both sides I am doing this. I am not claiming the left side is 0. Okay. So far it is so good. So now I am expressing this like I did some differential, I mean converted this derivative to that.
Right.
So this is the seventh equation. You see again p square, which is a part of the parameter, kinematical invariant. For more, if you have more legs, there will be derivative with respect to pi dot pj.
This is somehow the condition that the whole diagram depends only on p square.
Only why p square, sorry, on the masses?
And the mass square, but no, but the Lorentzian bending structure is only.
No, but for example, if you have three loops, then you have more Lorentz structures, right?
Then you have more.
More kinematical invariance. 3 legs, for example, pi dot pj, pj dot pk, something like that.
Right, but then p dot del p won't be just p square itself.
No, it will be different. This diagram we are
So
safe.
in this particular equation is somehow giving you the statement that the whole thing depends only on p square.
Yes.
And that propagator by propagator is not true. And but it fills it up. Yeah.
Subhajit, can I understand the last bit you were saying that your integral is a homogeneous function
Yes.
of all your variables?
Yes.
In your variable space.
Yes.
And then there's a particular differential operator which undulates it.
Yes.
And just from the fact that it's a homogeneous function with a particular degree.
Yes.
And then you just use that to get that one more. Is that right?
No, I mean, what I am doing, I am operating this integrand both sides with the same thing, and the left hand side I am just converting into these things. For example, p del p, this I can write like this, right? Del p square, sorry.
Yeah.
You understand the algebra, you want to interpret.
Interpretation, I think what Shiraz told actually, that this only depends on this particular kinematical invariant, p square.
But this uses the fact that the integrand is homogeneous function, right? Of this of the
No. It just uses the fact that the final external vector is only p. So we're not saying anything about the dependence on the masses. But just the dependence on p because it's a vector has to be p square.
The invariant.
Okay.
Is there an integral there on the equation or not?
Yeah. Integral is always there.
There's no difference. Right hand side, there should be an item.
Yeah, that should be it.
Yeah. Sorry. Okay. Good. So
So this integral of p dot del p goes into the source.
yes. I mean, whatever it generates, it will give you.
And if you write it as that kind of an equation.
Yes. And this will again be x6, for example, x1 to x5 are 5 mass square, and this is x6, and this is derivative with respect to x6.
And once again the derivative with respect to p will pull out stuff in the numerator.
And then that,
you will get it.
yeah. This is the idea.
Yeah. Very nice. Very clever.
And you said you have 7 mass parameters.
No, 6.
Six.
Six
Six.
parameters, 7
Okay, no, yeah,
directly
yeah.
1 minus.
Yes,
Yeah,
exactly.
6 mass parameters. So 2 of the mass parameters of the indwelling the outgoing moment you are taking to be the same, right?
Yeah, because momentum conservation, right?
No. Okay, yeah. But in principle, you could have different masses for the different. I mean, let's say you have two interacting particles, and you have some. Let's say phi 1, phi 2. You could have.
But then on-shell diagram of this sort could take this. Because if P1 is same as P2, then P1 square is same as P2.
Yeah.
And if you even do that, it will give the same equation,
So it's
right?
all on-shell. That's
Oh,
it.
fine.
Oh, so this is the kite, and this is the kite integral. I have taken this routing of p to write the integral like this. So, I have 5 propagators. I have 2 loops and I have this p coming in, and my mass squares are x1, x2, x3, x4, x5 and p. This is the parameter space, and L1 and L2 are the loop momenta, and this, so this will be the associated integral with this diagram.
What is this convention? You are drawing additional lines to do what?
Which additional line? This one? This is routing, I mean just to express the diagram. I am taking it to be downstairs.
Not down line.
No, no, the whole line. No, no, no large n.
So almost like okay. Yeah.
Okay. So, as I explained, so this is the parameter set, and as there are, we are considering d dimensions, 2 loops, so 2d upstairs and 5 propagators, so 10 downstairs. So, this is the dimension of the integral, this is the side. So, there is some particular symmetry associated with this this diagram, because so suppose you consider an imaginary line like this diameter goes into itself and like this. So, the symmetry of this diagram is like this. Okay. And as I told you earlier that the if you change the loop momenta and you get the equations in the parameter space and the associated group G. So, for this particular integral, the group, the Lie group associated with this diagram, which acts on the parameter space, is this, which is the upper triangular invertible matrix actually.
How did you figure that?
Because so you have different operators I have wrote here, right?
You've written 7 operators.
7 operators. So, the 7 operators looks like this.
Okay. Is that upper triangle?
Yeah, I mean block.
Block, right? Fine.
Not exactly upper triangle.
Fine. Okay. So you say that if you take the commutation relation of these 7 operators, you'll get the same as the commutation relation as
Yes, yes,
as this thing closes.
yes, I think so.
Isn't that fine a little bit?
I think that's it, right? If you draw the blocks, how is this block of a triangle?
So it closes. Okay.
I'm sorry, which matrix are you drawing here?
These generators, I have counted you 7 generators, right?
The TA, J, D by D. The
Yes,
TA,
yes.
J's are what you're drawing. So that's a 6 by 7 grid.
Yes,
Yeah. Okay, so.
these are the generators.
No, I think he's saying that the algebra of the generator, the full differential operator, is the same as the algebra of this subgroup of matrices.
You consider that dA, this Ca times T, that thing, A index, you consider that dA, that algebra actually.
Are these the generators or are these the loopers?
Which one?
Because G, loop is the subgroup of the upper line of the loop. So the
This G is the associated Lie group with this diagram.
Yeah, so the generators say you also probably the upper line.
Now the 7 generators basically fall into this form.
See, when you multiply block upper triangle matrix, you get block upper triangle. But in the generators, you have the combination.
His question is, are you looking at infinitesimals when you make this matrix or finite?
I looking at infinitesimal.
But the G represents the group.
Yeah, this is the Lie group. I mean not discrete group.
The algebra.
Lie algebra. Huh.
Algebra.
Algebra. Sorry.
Yeah. But maybe he means that it's the generators of that.
No.
matrix.
So
these are the forces that you can use.
No, no, I am talking about this, this
Just on the left hand.
left hand side. dA you can,
Only, okay, okay.
only the left hand side.
Only the algebra of the differential operator.
Yes, yes, yes.
We need the sources.
Sorry, Subhajit, can you just repeat what is this PL and minus 1? So you have a L cross L block.
Yes, 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 yes. So the first block is of size L and the second one is like this, n minus 1. So here for this case it is like this, you see.
Right? So but the thing that you have drawn, it has it is not completely upper triangular.
No, no, not completely upper triangular, it is block upper triangular.
This is what I try to understand. What do you mean? So for this means the 2 cross 2 matrix can be anything.
Yes,
Right? In the first 2 cross 2 there is a general block.
yes,
And then you know like the last row has only no things until diagonal. Is that the statement?
we can,
Wait, so the PL comma n minus 1 will be a general L cross L block, and then there are n minus 1 rows which where you know like everything is 0 until you reach the diagonal. Is that what I can understand in PL comma n minus 1?
I,
Just two blocks. Block upper diagonal. Upper diagonal, sorry.
yes.
So there are two blocks in the diagonal of sizes L and n minus 1 respectively.
Yes.
The remaining part you just fill up according to the
Think so. Just let me think.
So this way we'll always get a square matrix. L plus n minus 1 by n plus n.
When you take the commutator,
No, the full matrix. More than that. Look them in that three blocks.
yes,
You just get a square matrix of one side equal to L plus n.
yes, I think so. I think so. I think so.
Sorry. PL n minus 1, what is the dimension of this? What is this matrix? In general, it's L cross n minus 1.
No, it's L plus n minus 1.
Cross L plus n minus 1.
Number of external states. No, can't be. Because then it will be. Yeah, right, that's right. Two external lengths. So
How would that block upper diagonal matrix look?
I mean, you want the generators or?
Definition of the notation.
What is the definition of E n comma m?
I mean, I would think it like this, right? I mean,
First of all, what is the dimension of Pn comma n? What matrix is it? How many locus and how many locus?
I think. I'm sorry, not understanding. Yeah, yeah.
Maybe sorry.
No, no.
So I think he's just talking about
where m is n minus 1.
yeah. And then this is just
Something.
times n, and this is
This is
and
equal to
n.
So what is this PL comma m?
Yeah, this is set of all these matrices is
And remember that m is n minus 1.
yeah.
Yeah.
So all these blocks except the one which is 1 0 can be 1 0.
Right.
Yes, yes.
And I think you should think of it this way, that the L cross L is del by del Ki of Kj. Then the L cross M,
So it's L by del L,
Li of L.
the root root.
Yes. Then the L cross M,
P dot L del del L.
exactly,
Yeah.
P dot del by del.
And this is P dot del del P.
And then this is the M cross M is the more clever thing that you.
Yeah, yeah.
Similarly, no, I think construct a differential operator for the zero block also, right?
Which is what?
K del by del.
No, no, del del P is not allowed. That is not the symmetry of the
You
integral.
put it inside the integral and integrate to get this.
Yeah. That one, yeah. Otherwise, we had all 9 equations.
Yeah.
That we have 7 equations, right?
Yeah. Okay, great.
Okay. So now, as we have to, I mean, for a particular diagram, it is most useful when this potential numerators are not there or in less number. So we count how many kinematical invariants can be built out of the momentums. So there are this 1, 2, 3, 4, 5, 6, and you can see there are 5 propagators and 1 p square itself. So the quotient is 0. So for there are no potential numerator, that means all of the thing which will come in the numerator while differentiating can be expressed in terms of all the either the propagators or the external momentum. That's why this is 0.
Fantastic.
So this p square comes from the external.
The external momentum.
So it's necessary that you take the non-amplitude.
Yes. For the loop diagram, this p square won't be there. I mean, bubble, vacuum bubble, and so on.
So amplitude, non-amplitude, what makes it? I mean, it's just as a
Just use it.
argument. Yeah, use it.
So the source comes and then we use the amplitude.
Exactly. Yeah. So it's basically amplitude.
Okay, fine.
Yeah.
Yeah. So you see the dimension of for this diagram, the dimension of this group is 7. Yeah, so this we talked about. And two, I mean, I can differentiate. I mean, I told you that all the generators of the equations are looks like this. But to make the equation look nice, I have taken some linear combinations. Okay. So I consider this kind of these 7 equations, which will be again will look like this, and I will explain for this kite diagram what the CA, this T matrix is, and J is. Then I complete my equations, right? So with this linear combination of the generators, the CA looks like this. This is good looking, you see. And the Tx matrix looks like this, where this S means this for simplicity I have looked like this to make it this block and block and block.
Yeah, and the fact that you have as many differential equations as parameters or more tells you that if you know the integral at one point, in principle you can get to it.
Exactly. As the codimension here is 0, the codimension of the g orbit is 0. You can, if you can find at a base point the value of the integral by some other methods and so on. For example, this Schwinger param, all mass. No, you have. I mean, for example, we will be solving this equation at a particular locus. So that will be a cubic polynomial, which is known as Bykov polynomial. So if you set all the masses except the middle one 0, then the integral is very easy. You can just evaluate the integral with the Schwinger parameterization or the Merin-Barth and all kinds of things, and get in principle the integral in anywhere you can explore the parameter space with a line integral. Yes.
And if it's greater than, then you have these added.
Exactly.
And just one more point, in order to solve the differential equation, you also have to say something about the homogeneous.
Exactly, I will tell you. Yeah. So this is the Tx matrix, and these are the dependencies, and the sources are like this. Let me explain the sources. By O, I mean that propagator is omitted from the integral, and d of something means I take derivative with respect to something. For example, this whenever you see O5, that is this thing, and del 3 of that means I take derivative with respect to this. So there are 2 kinds of sources, as I explained to you. One is propagating Seagull and one is the figure 8 diagram. Okay.
Sorry, Subhajit?
Yes, Logan.
Up to is same as O down to.
It is always down. Sorry.
I think the answer is yes.
Yes, because you omit. I mean, whenever you see something associated with O, you just just remove it. If you remove the 5, the middle one, it will give you figure 8, and if you remove any other 4 you will get propagator signal. Okay. Are you happy, Loga, now? Yeah. Yeah. So now, as I told you, there is a theorem in linear algebra that you can always, as Shiraz told, that if there are, I mean, seven equation in 6 parameters, there is only one can find a maximal minor, and that is a left null vector. So using these things, one can show that this maximal minor can be decomposed into an invariant times that the null vector times some algebraic some polynomial. Okay.
So what is the statement about the G orbit? So ideally what you want is for the G orbit to span the whole parameter space?
Yes. No, now I will show you that for a particular locus in the parameter space, the integral is not even a line integral, that is a linear combination of simpler diagrams. So that is B3 is equal to 0. This is a cubic polynomial. One might ask that from where you got this polynomial, from sky. It is not like that. So you can I mean you can factorize these maximal minors in this kind of fashion. It will be a product of the stabilizer, by that I mean the null vector, times the invariant, times the some number or some polynomial. So for example, in this diagram, for example, I can give you a physical motivation. So suppose
Subhajit?
Yes.
Sorry, just to understand. So the B3 is a polynomial which is annihilated by this Tx.
No, not quite. It will be annihilated by the constant free. There will be, I mean, from the 7 equations, you can generate 5 equations which will have this C is 0. It is an invariant of that actually, to be more precise.
It's not annihilated by the generator?
No.
B3?
Not quite. Because when you will find the homogeneous solution, you will take the constant free subgroup, right? And then you will show that it is a function of these two group invariants. So it is not annihilated by T, but it is annihilated by the constant free. You can consider a sub matrix. I mean, you can take 5 equations where you can drop these C's, and P square and B3 are annihilated by that constant free matrix actually, times the
B3 constant along G orbit?
B3 no, I mean at B3 is equal to 0, I will find the solution. That is the locus, algebraic locus.
So then I'm not understanding why B3 is an invariant if it is not annihilated by the G generation.
No, B3 is an invariant of the constant free group, not this G.
Constant free group?
Yes, I will tell you what is that. Because if you write these 7 equations, all of the equations are not, I mean, you can find a linear combination, maximally 5 equations you can make where the constant is 0. That 5 cross 6 T, I mean that group, B3 and P square is invariant of that. It is not of this whole thing.
What is the constant?
C.
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 It is D minus 2 or you see like this. You can see that all of them are non-zero. So not like that. You can take linear combination and make 5 of them 0, but you cannot make all of them to 0. Maximum 5. So I mean there will be 5 equation, and that T, call that TCF, constant free. P square and B3 will be invariant of that thing.
So the number of things is just the number of things that are annihilated with T. So here the point is that you have 7 but 22 linearly independent guys, D minus 4 and 2D minus 10, and then
Yes.
you are saying there are 5.
Yes, absolutely. So yeah, so Abhijit's question. So suppose you consider this diagram, it looks like kite, right? Suppose you take a vacuum closure of that, you just close it, it is a tetrahedron. So you will see, for example, let me give an example. For example, suppose you are given 3 sides of a triangle, the Heron-Kallen formula, x square plus y square plus z square minus 2xy 2yz 2z. it is the squared of that triangle, right. For example, if you take this B3, this is the volume of the dual tetrahedron of made out of the vacuum closure of this. Dual means the face and vertices are interchanged. You close it, you have to imagine. It is a tetrahedron. Yeah, I am closing it. The vacuum closure is a tetrahedron. Right? Yeah. I am saying yeah.
Is there a property of this thing, or is that like a more general statement?
It's a more general statement, as I told you, that the maximal minor can be factorized into this B3 P square and the left hand side null vector.
And B3 or the analog of that is always like the volume of
Yes. This is the Bykov polynomial.
external legs, like that 3, maybe you have different vacuum closures, is that not possible?
No. You are asking will always the vacuum closure will motivate you what the invariant is? No, I don't think so. For this case, it was. Yeah.
I'm sorry, I'm getting a little lost about all this and stuff.
Yes.
So I thought that KA was your null vector.
Yes.
And then you multiply your equation above there in the
Yes.
chalk
Yeah.
by KA from the left.
Yes.
And if there's a difference between the operator part,
Yes.
and you get KA, CA, I is equal to.
No. See, there are two stabilizers. For example, this is a 7 cross 6 matrix, right? So as Shiraz said, there will be one vector which will give a linear combination of this. So if you take the maximal minor, that will give us 7 dimensional thing. So now if you set, you have to take next to maximal minor to find this at what will this K is not the global stabilizer. So the global stabilizer is like this. Now this K, the K which Shiraz pointed out, there you will see that Ka dot Ca is 0. That only gives you a condition between the propagating seagull and the figure 8.
Because KA, CA is 0, so you have to do more. Right? Okay.
Yeah, exactly. You have to go to next maximal minor.
But what property does this next maximum minor have?
Next maximal minor has the property that it can be factorized in terms of the group invariant times, times the stabilizer. Stabilizer means
Sorry, when you dot this with T, what happens?
this when I dot with T, this T vanishes, but the C doesn't.
But why is there a second thing for which the T vanishes?
Because now I am moving further in the parameter space, right? I am setting a constant. Now the rank of Tx won't be 6 anymore, it will be 4.
Okay, so you are working in a
Particular locus.
Okay, looking for those x's for which this happens.
Yes. Yes.
So KA is annihilated by the constant T.
But you see that, no. This Ka is the new Ka, but it will again annihilate this T matrix, because you see, no, what is the question, sorry?
No, so when you're talking about B3,
Uh-huh.
you said that B3 is the invariant of the
Constant free, yes.
part of the space.
Yes.
So is the KA annihilated by the T that
No, if you even go to the next maximal minor, I am always taking next maximal minor from the original Tx. Otherwise, constant free group is this much. It won't give you that.
Yeah, you're going to define this T. I still haven't understood exactly what T is. So you'll define this.
Yes.
I can multiply that KA with anything I want, right? It will still be answer.
Of course.
So are you going to assume I will consider this particular factors for KA?
No, if you take the maximal minor, it can be expressed in this product. This maximal minor is a constant thing, right? If you multiply both sides, that's a different case.
Wait, now I'm sorry. This what maximal minor?
Maximal minor means this Tx matrix, there are 6 parameters, so 6 derivatives, and 7 equations.
Yeah.
This is 7 cross 6 matrix.
Yeah.
So the maximal minor will be 6 cross 6. If you generate this, you will get a vector that is the global stabilizer, which will annihilate the Tx as well as the C. So that will set a condition on the external on the sources. Now if you go next to maximal minor, that will be 5 cross 5 from this Tx, that will again annihilate the Tx matrix, but won't annihilate the C. That will produce the algebraic solution, because in the denominator if you have Ka dot Ca 0, that means nothing, right?
But it won't annihilate T for all values of x. It will
No, only annihilate when B3 is equal to 0. Exactly. At some particular locus in the parameter space, I am finding this solution, and the solution is algebraic now.
So you said this equation is defined by the fact that MA is well defined, therefore this is right.
Yes, 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 yes.
But then this method will work only for some specific sets of x's.
Specific sets of x's, as it will produce the algebraic solution, but the line integral is always valid.
So this is the maximum minor.
This is the maximal minor.
CA dot MA, that is CA MA is zero. That's it.
CA is not.
This
I-
one I think will be set.
No, this here CAMA will not be 0. No, 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 no. There are two things. One is global stabilizer, which is the maximal minor, and one is next to maximal minor.
So what is MA?
What is MA?
MA is the next to maximal minor.
This, I mean, MA vanishes anyway when B3 is 0, right? So what is the condition?
This is not a condition. I mean, suppose one asks that how will I know such a Ka which will annihilate my Tx matrix but won't annihilate the constants. This is a way to get that. You will compare many equations like this, and you will, from that you will understand that what K is.
So if we just multiply MA by that equation,
Yes,
what are we getting?
I am getting this non-zero, this 0, this non-zero.
Why is the second thing 0? Because we are imagining B3 as 0.
No, 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 no. This K has that property. Next to maximal minor always also will annihilate the Tx matrix. Not for all, for B3 equal to 0.
But equal to everything is 0.
KA will annihilate. KA dot CA is 0 when B3 is 0.
But Ka dot Ca is not 0. You see, I am not multiplying with MA, I am multiplying with Ka.
And how do I know that this is some
This is the theorem.
that when B3 is 0, K will still?
I mean, that's what it gives actually. If you go to next maximal minors, the factorization is such that some polynomial, some orbit which equal to 0 it will work times that stabilizer. It is a theorem.
A runs from 1 to 7.
K runs from 1 to 6 or 1 to 7. It will multiply the Tx matrix, whatever that is. So, 7.
So what I don't even understand what you mean by next to maximum. I mean, I understand a minor is the thing that a particular matrix element
Yeah, let me tell.
multiplies itself.
So, there is 7, there is 6, right?
Yeah.
So, this is maximal minor. Many of them.
7-dimensional
7.
picture of it.
Yes, yes.
Okay, good.
Yes.
That I understand. Now,
Next to maximal minor means I have to go find 5 cross 5.
yeah, so that looks like there are plenty of those, right?
Yes.
So why is there just an A in there? Why are there 7 of them?
Actually, there are in this case there will be 2 stabilizers, and the equation will look like this. There will be 2 indices. I mean, I have not written that probably. Let me tell you.
That A, you say A 1, 2.
Just let me tell you. Then there will be a wedge product between 2 stabilizers actually.
Sounds like 7 into 2 or maybe 7 into 3 by 2. Yeah,
It will be something like,
something like that. But yeah.
I mean, now you see, when you have maximal minor, there is 1 free index, but when you will go 5 cross 5, there will be 2 index.
Right.
So that will look like this.
So this A is the third index.
A is a third index, exactly, like this.
Okay, so it's A runs over many values.
many variables.
Okay,
Yes,
fine.
yes. Okay. So this is somehow, I mean, you can imagine is it to be dual, I mean, volume square of a dual tetrahedron, which you can
Subhajit, just one warning, since we have this lunch now,
oh, sorry.
you know, the time is a little serious.
So let me wind up fast.
10 minutes.
Yeah. Okay. Okay. So the, I mean, that is an interpretation of this B3 that is called Bikov polynomial in literature. Oh. So so at B3 equal to 0, this is the thing. Just a moment. This is okay. Good. So the first maximal minors, which has only one index, will give you this thing. This, if you multiply, it will annihilate C, annihilate T, and only give a relation between K dot J. Okay. And for simplicity, there is, I mean, if you just write it, these are very long, but fortunately these are much symmetric. I mean, these are can be obtained by the derivative of B3 and this lambda, which is this thing, and so on. Okay. So as I said, that it will give a constraint on the sources, and also as I told you earlier, that the parameter space is 6 dimensional and the rank of this P is 6 dimensional. So one can move anywhere in the parameter space. So now I am going towards the homogeneous solution. So the homogeneous solution, I took linear combinations like this. So here you will see that the group is, I mean, the new, I mean, if you impose, I mean now there will be two invariants actually. Just let me tell you. Yes, if you consider the constant free subgroup, the rank of that it will be 4. So it says that there must be two group invariants, because the parameter space was 6 and the rank of that matrix is 4. So there are two group invariants, but again you can systematically derive, you can go to next maximal minors and can see that there are two group invariants. So the homogeneous solution will be functions of these two invariants, P square and this Bikov polynomial, and now it has to satisfy also the equation with the constants. So that gives the homogeneous solution, right. So now we are going to next maximal minors, where this B3 equal to 0 or P square equal to 0. Now we will find another additional stabilizer which won't annihilate this C, but will annihilate this, and we will get an algebraic solution. So for B3 is equal to 0, we get two this kind of stabilizers. So if we multiply a linear combination of this from the left hand side, we will get something here, nothing from here. So that will give an algebraic solution, right. And there are some checks. So in earlier literature, in this second post-Newtonian, as I said, this diagram was used. So there all the masses except the inflowing momenta was 0. So there the solution was only given in terms of the one propagating seagull and one figure 8. So if you take that limit, our diagram goes to that. And also there are another interesting case done in previous times, where 3 mass scales were 0, and at B3 equal to 0, there it is called some diamond rule and so on. I mean, this also matches with our computation. And also P square equal to 0 locus is a bit simpler, because if you set P square equal to 0, it is again the diameter diagram, which is not very interesting. But for the sake of complicity, we determine the stabilizers again, which will again give the algebraic solution, and that also matches with the solution of the diameter. So this is another consistency check. So yes, of course. Those can be calculated. I mean, some collaborators are doing that actually. Some figure 8 is very easy, but the propagating seagull is a bit involved. So that is being done.
So you can't use the same method on that to reduce it even further?
Is the same method is applied actually. Same method is applied, yes. Yeah. So this is also a consistency check. What we have done, the g orbits were found to be 6 dimensional in our 6D parameter space. So this means that the SFI method is maximally effective in this diagram. So and all the on the surface where this cubic polynomial vanishes, we were able to express this integral in terms of only algebraic linear combination of simpler diagrams. Okay.
Now, could you solve the differential equation to get the diagram at a generic point?
Generic point, then one has to calculate that as a base point. For example,
You have to calculate this line integral.
yes, yes,
Can you solve that?
I can solve that, but I haven't done that yet actually.
But it's possible. It's not always easy to solve these differential equations.
No, I think it can be done, yeah, but I haven't done that yet. So mainly this is the central result actually. So there is another important thing that I have said, that you multiplied with something and you say and you see that the propagating seagull and the figure 8 diagram has some constraint. So if you use the SFI equations for the propagating seagull or the figure 8 diagram again, you will see that many parts of k dot j is going to 0, but not quite, but it should be. So it means that we are missing, I mean some other collaborators are working on this SFI equation on propagating seagull. Probably one equation is missing or not, but one should explicitly could demonstrate that k dot j is exactly vanishing, not from this, from that their equations also, right. And also what Shiraz pointed out, that if and a good base point will be starting with this except the middle line. If we can calculate by Schwinger parameterization and so on, one could able to solve as a line integral for the other yeah. So thank you for your attention. Sorry for taking longer time.
So you were saying that your definition of when you said the SFI method was useful.
Yes.
You were, basically the main argument is that
That the dimension of that group.
You can again just in principle, given all of these equations, you can compute if you can compute the integral at one point in parameter space.
Yes.
Then you can compute it on any other point.
Yes, but provided that you have to express that, I mean not always you will get so much equation that you will be able to do that.
Right. So it's useful when that, but even if you don't.
Suppose you have one equation, what will you do?
Right, but then you can still, maybe if I can compute it on one point, I can compute.
No, that equation will not be that is a mixed equation, right? There will be derivative with respect to del x1, del x2, del x3, del x4, many things. It's a coupled, I mean.
You're saying along some line you can compute it.
Right. So I'm saying when that's funny term. Suppose that I'm in a point in parameter space where that point is that x.
Then you can always
So you
get.
can still use this method to derive it in some subspace.
Yes, of course. Yes. What is your question? Sorry, can you speak up? Huh?
So there's this thing where if you have like powers of loose momenta in the numerator,
Huh.
you can always reduce diagrams like that to diagrams which have no loose momenta in the numerator.
Yes. I mean the idea is that you have to take a clever linear combination which removes that thing from the. Then you will have less number of equations, but you can always something you can do with less, unless it is one equation.
Sorry, I get my question. So there is a notion of like a basis. So there is a certain set of integrals that are like enough to like talk about integrals of a particular class. I was just wondering if using these techniques also,
Huh.
one can sort of illustrate a kind of basis for situations where this is not maximally effective, but can sort of sub-maximally effective. Because we like you always get an equation. It's just that the sources might not be simple.
Oh, so you are asking that in the sources, some complicated sources which I won't call it simple, whether you can do something with those things. By, I mean, I am considering one diagram, right? What do you mean by basis?
I'm talking about the method itself.
Uh-huh.
I'm talking about a situation where it is not maximally effective, but the co-dimension of the G orbit
Is not zero, huh?
but is something else.
And then what? Sorry.
And I was just wondering if there is some minimal set of
Yeah, always you can cleverly do some things, but that won't be falling in this particular method or category, right? I mean, suppose it does not give you something, then you are doing something else.
So I should know this, but this basis, what is it? For instance, it's basis for given loop order?
Yeah. So I think what it says that I think there are like triangle, box, there is a particular set of diagrams. I can't do those very well either, but
Given diagrams and given loop order, you can write some basic set of diagrams.
always write it in terms of
And,
bubbles, the bubbles, triangles, and boxes.
Oh,
Something like that. Up to one loop is either
there is a diagram, there is a chart actually.
right.
So on the right hand side you have more vertices, and the left hand side you have which can source that. So we are just completing that chart actually. I can show you the chart actually.
Right.
And I see. And your question was, can you work systematically in this basis, and in this basis get an arithmetic equation?
Yes, I understand now.
The vague memory of hearing a talk who said that this basis is well understood only at finite viewpoints. That you go higher and higher, it becomes more complicated.
One loop or something.
One loop, yeah, finite
Sorry.
viewpoints.
So the number of basis elements in proof.
Yeah, I'm not even sure that they understand how to, that prove that there is a loop. So, since this is relating loops not equal to 1 to loops equal to 1, everybody may be correct. Maybe not.
You see, this is the tetrahedron, which is the vacuum closure of this. This is the vacuum signal. This is the propagating signal, which is the source of this. So many of them are complete. So I am looking at this actually, and on all of the right hand side can be expressed in terms of the left hand. This is just a complete set of up to 4 vertices what can be done, and loops this way and number of vertices that way, something like that.
So how much more? It seems like if I now start doing for vector fields with extra indices, then it seems like, because it seems like the only way to work is the numerator has to be a scalar, right? Otherwise you
No,
can't
now
use the
you will
denominator.
make you will multiply upstairs and downstairs by p slash minus m, right? Then upstairs will again be a number, kind of.
No, let me think of it for a vector field. So the denominators are all just scalars.
Yes.
Or just some k squared plus m squared. Now the numerator contains vector indices.
Dotted with polar elements.
Dotted with polarization.
So
It
again
will never
number.
cancel the denominators, right? Or
Yeah, I was wondering the same thing. I was wondering in this twistor way of thinking whether there is. Because the point of the twistor thing is that same data goes into the polarization as in the momentum. So there may be some clever way of.
When you put standard tensor, reducing tensor integrals to scalar integrals, the Parthenon benchmark, into one loop. I think we can generalize it to this question of saying that the final integral should only be some particular tensor structure and then
Time to
that,
scale.